So, hello everyone. My name is Arthur Pellegrino. I'm an AI fellow at ENS in Paris. And today I'm going to present some joint work with Alex Krakogaic on defining similarity metrics between different neural networks, and in particular using tools from Riemannian geometry and statistics. So the field of AI has been experiencing a current push towards mechanistic interpretability, trying to understand the computations performed by neural networks. And some of these ideas, they are actually dating a couple decades back. And one example that I like to start my talk with is some very simple analysis of the geometry of a convolutional neural network. So in this work from at NeurIPS back in 2012, what they did was they took a deep convolutional neural network and they asked how this neural network was representing different variables of images in its activation. And to probe for that, what they did was that they constructed a set of images to present to the network where they varied one variable of the image at a time. So for example, here the position of the object in the scene. And so what they did was that they passed these different inputs to the convolutional neural network. They looked at the activation of a particular layer that they were interested in, and they repeated that for all these images to get a data matrix, so matrix of shape, number of neurons in this hidden layer by number of images passed. And to study how the network was representing this position variable in its activation, they did dimensionality reduction, in particular PCA, on this activation, to visualize this activation in a low-dimensional space, in a two-dimensional space. And so from this work, they drew several insights. So for example, it looks like at the center of this representation manifold, points are further apart, so space is magnified, and a few additional properties of this representation. So here, the key insight was that we could study this neural network, this very high-dimensional network, by studying the manifold or the geometry of its activation. And since then, this perspective has been extremely popular. So people have applied this view to language models, so applying the same tools to LLMs. And also, I'm interested in neuroscience, so applying the same tools to biological neurons, so the activation of biological neurons when a subject looks at images that have different features and how the brain reacts to those. More recently, there has been increasing interest in trying to understand the intrinsic geometry of this representation, the intrinsic geometry of these manifolds. And to explain what I mean by this, I'll show this example, this schematic of a manifold in pixel space. So we have a high-dimensional pixel space representing pixel of our images that we are passing to a network. And in particular, for the sake of argument, I'll consider, let's say, a manifold of faces, so images of faces. If I take two images on this manifold, these might be the two images that I have, and I might be interested in training a model on this data to try to generate new images. And perhaps the most naive thing that I can do is try to train a linear model, or even simpler, just try to interpolate between these images. And if I do that, I get something that's not quite good. So the image that I get is the hair doesn't really make sense. There are four eyes, and it's not great. Instead, if my model knows the manifold structure of the data, the nonlinear structure of the data, I can potentially generate a new image along this manifold of faces and get a quite good new image. I can have a qualitatively good model. And so this idea has been really pervasive recently. Very recently, there has been some work from Goodfire AI, which is a company into trying to understand the intrinsic geometry of LLMs. And so what they did in this work was that they took an LLM and they passed different prompts to this LLM where they varied one token at a time So for example, they passed the prompt, what is 4 days after a particular day? And a particular day can be Monday, Tuesday, Wednesday, and Thursday, right, and so on. And then they looked at the activation of this LLM, in a particular layer of this LLM. And here they are just visualizing it in a three-dimensional PCA space. And so what they did in this work was slightly more causal or of a manipulation study, in that they didn't stop there. They tried to infer the manifold over which these activations were lying, and it turned out to be a circular manifold because days of the week are periodic. And then they asked, okay, what if we take a new point on this manifold that doesn't correspond to any of those original days? So they took one of those black points, and from this activation ran the rest of the LLM and looked at the output of the LLM. And in particular, they did that in two ways. So they did this manipulation along the manifold, or extrinsically by just doing this linear interpolation between two activations. And so they looked at the output of the LLM for these different activations in this intermediate layer for this, what they call nonlinear steering and linear steering. And for the nonlinear steering, what you expect happens. So if you start with the day Friday, so you look at the activation when you say what is 4 days after Friday, you get that the most probable next token is Tuesday. And as you continuously vary the activation of this network along the manifold, the probability of this token will decrease, and instead it's going to be another day that's going to become more probable. And instead, when you do this linear steering, so you don't know about the nonlinear manifold structure of the activation, you don't get this effect. So that suggests that perhaps the intrinsic geometry of manifolds of activation can be insightful to understand how network works, but also to manipulate their output to have better alignment. So another example that I quite like of this is somewhat simpler. So this is a deep network, but trained on a very simple task where inputs are just two-dimensional. So layer 0 would be the input layer. And the network, the task that the network is trained on is to classify the blue and red point. So it's a binary classification task. And what they did was to look at the intrinsic geometry of this manifold using tools that I will explain later across the different layers of the network. And what they found was that progressively across layers, the intrinsic geometry of the layer was being warped such that the two classes were becoming linearly separable. So that suggests that there is really a link between the task that the network is trained to do, the computations that the network is trained to do, and the intrinsic geometry of its hidden layer. So now the question that I'll try to answer today is, how can we compare the intrinsic geometries of two different networks? So if I have two different networks that are solving the same task but in different ways, how can I quantitatively compare their activations and their geometries? So the picture to keep in mind for the rest of the talk is that we have a fixed input data manifold, so here two-dimensional, and we have two networks, two models, maybe with different architectures, maybe with different depth, width, and so on. And we are interested in comparing the activation of these two networks in response to this same input data. So we have two manifold of activations in these two networks, and we want to somehow define a distance or a similarity between them. And the way we are going to tackle this problem today is by defining a new similarity metric, MSA, between the Riemannian or intrinsic geometries of these two networks, of the activation of these two networks. And so that's the kind of general goal of what I will present today. So the outline of the talk is as follows. First, I will start by reviewing other similarity metrics for neural activations that are not based on Riemannian geometry. Then I will present the mathematics behind our new similarity or distance function between Riemannian manifolds. And then I'll show some applications to diffusion, classification, and if I have time, perhaps NeuroAI. So the broad question that we are trying to answer is how we can compare different neural manifolds or different representational manifolds in different networks. So the way previous work has tackled this problem was as follows. So suppose you have a manifold in activation space. So here I'm showing a three-dimensional space where each axis is the activation of one unit in my hidden layer. And I'm looking at the activation in response to different inputs. And here, just as in the case of the LLM that I've shown at the beginning, it lies on a circle. Then what these methods have done is to just pass these different inputs to the network and record the activation vector and put that into a matrix. And then ask the question, how can we quantify whether two other manifolds coming from two other networks, which one is closer to the first one? So here, the first insight is that we are really passing the same inputs to the two networks, but the two networks might have, for example, different number of hidden units and different architectures and so on. And we want to have, or these works wanted to have a way to quantify the similarity between X and X2 and X3. So to define this similarity, so this time between these matrices that represent the activation of the network, people have taken very different approaches. So one of the simplest one that I like to start with is the so-called processes analysis. So we have two activation matrices from our two networks, X1 and X2. And to define the distance between these two matrices or these two representations, what we are going to do is rotate one into the other to try to minimize the Frobenius norm between their difference. So we are going to rotate one representation into the other and compute the minimum Frobenius distance over these possible representations. Another popular approach is the so-called representational similarity analysis. So here, what RSA is based on is to first compute a covariance matrix for each network separately. And this is a covariance matrix of shape number of inputs by number of inputs. So it's not the neural covariance, but the input covariance. And then define some similarity metric between the covariances themselves in terms of the trace and the Frobenius norm of these covariance matrices. Yet another approach introduced by Jeff Hinton was centered kernel alignment, which is a very similar idea as RSA, but instead of computing a covariance matrix, they use a kernel. So they map the data to an RKHS first, and then measure the distance between the data matrices in this RKHS. Okay. So these different methods, they have various properties, slightly different properties that may or may not be desirable depending on the application that you have at hand. But the big picture goal of these similarity or distance measures is as follows. So we have two representations. So here defined in terms of matrices and later defined in terms of functions. And we want to define a distance or dissimilarity between them. And there are several properties that we want our similarity measure to have. So for example, we want it to be symmetric and to be a proper distance so that it is symmetric, so that the distance between x and y is the same as the distance between y and x. I might also want it to be invariant to some transformations. So if I have two networks that only differ by a rotation, whose activation only differs by rotation or permutation, it probably means that these two networks, they are performing very similar computations, meaning that I want the distance from x and some rotated neural space times y to be the same as the distance from between x and y. And finally, another property that I might want to have is for it to be bounded or normalized. So I want the number to be interpretable. I don't want to say the distance is 1000. That's not very interpretable. I want it to be bounded and properly normalized. And in particular, what this normalization will allow us to do is to transition between a distance function and a similarity. So distance would mean that the higher value means more dissimilar. Okay. So I kind of skimmed over that first property, but I'll be more precise now. So we want this distance function to be a proper distance, mathematically speaking. So it must follow some axioms or some properties. So the first one is positivity. So I want the distance between x and y to be greater than or equal to 0, and to be 0 if and only if x and y are the same. I want it to be symmetric, as I've mentioned, and perhaps most importantly, I want it to follow the triangle inequality. So how does that look like? So if I have three different networks that have three different activation matrices, x, y, and z, I want the distance between x and z to be less than or equal to the sum of the distances between x and y and z. And if my distance measure satisfies these properties, then, so some methods satisfy these properties. CCA and RSA are examples of methods that don't. Procrustes is an example of method that does. But if we do satisfy these properties, what that means is that we've really defined a topological metric space on the space of possible activations of neural networks. So we've defined a space of possible representation in a mathematical sense. Okay. So one feature of existing method is that they focus on the extrinsic geometry of neural representations. So for example, Procrustes, as I've mentioned, just takes the neural space and rotates it, or takes the manifold and rotates it to align it with the other, and then just measures the Euclidean distance between points. And as we've seen at the beginning, it is often the case that the extrinsic geometry of neural representations is not the best characterization of the computations performed by a network. Oftentimes, it is the intrinsic geometry that is more insightful. So we want to define a similarity metric that is aware of the intrinsic geometry of the manifold. So one question that you might ask is, okay, does that matter at all? Is there a strong correlation between them, such that if the intrinsic geometry is similar to the extrinsic geometry, then it must be that, if the intrinsic geometry of two networks is similar, it must be that the extrinsic geometry is similar, and vice versa. And it turns out to not be the case. So I'll show examples of this now. So here, this is just a toy example. These are real results, but not from a neural network. I've just handcrafted these manifolds. And I'm going to ask what is the similarity between these two different manifolds, either from an extrinsic or intrinsic standpoint. So extrinsically, these two manifolds are quite different, because if I measure the Frobenius distance between pairs of points on this manifold, they are quite far apart. But intrinsically, these two manifolds are exactly the same, because the angles along the manifold and the distances along the manifold, they are equal. So the intrinsic geometry is exactly the same. And to be slightly more concrete, so by extrinsic geometry, what I meant here is Procrustes, so aligning and then measuring the Frobenius norm or the Euclidean distance. And by intrinsic, I meant MSA, which is the new method that we are proposing and that I will explain next. And it turns out that the converse is also true. So you can find examples of manifolds whose extrinsic geometry is very similar, but whose extrinsic geometry are quite dissimilar. So at the beginning, we saw that in several examples that the intrinsic geometry was more insightful as to neural computations. And here it turns out that the relationship between the extrinsic and the extrinsic similarity can be quite weak, such that to really understand better neural computations, we really need to define a new intrinsic similarity metric. Okay, so slightly more generally, the limitations of current approaches for these similarity analyses are as follows. So like I've said, they focus on the extrinsic geometry of these neural representations. rather than the intrinsic geometry of the manifold. They don't really leverage the fact that the inputs are to a network can lie on a manifold, or that the activation of the network naturally lies on a manifold. They are just distances between matrices of activation. And they are sampling based. So the way they work is that you first pass different samples of inputs to your network and just record these different samples of activation and just compare the point clouds defined by these activations. So we want to go beyond these limitations. So for this, I want to be very precise into the way I'm going to define the similarity metric. And so I want everyone to be on the same page. So I thought it would be nice to have a one-slide review of Riemannian geometry. And in particular, the tool that we'll be interested in is the so-called pullback metric. So to define the pullback metric, we need a few objects. So I'll consider two manifolds, M and N, as well as a function f between them. And I'm going to endow the N manifold with a Riemannian metric G. So a Riemannian metric G at a particular point Q in the manifold is an object that takes two tangent vectors, so two elements of the tangent space of N, and returns their inner product, a real number. So visually, how does that look like? So we have our M and N manifolds. If we take two tangent vectors in our N manifold, so the red and yellow vectors on the right, we have a way to measure their inner product with G. And now, so we have access to the tangent space of our manifold M and the tangent space of our manifold N. And I want to somehow define an inner product back on the manifold M based on the one that I have on the manifold N. So it's going to work like this. So if I take a particular tangent vector V in my original manifold M, I can do the so-called push forward of this vector to get a tangent vector in the manifold N. And then once I'm in the manifold M, in the tangent space of the manifold N, I know how to take an inner product. So I can just measure the inner product. And this is precisely what the pullback metric is. So in local coordinate, so if you have coordinates on your manifold M, the way this push forward is represented is through the Jacobian of the function f. So you're just applying the Jacobian to your tangent vectors. So again, this is the Jacobian with respect to some local coordinates on the manifold M. Now to define the pullback metric, like I said, we have all the ingredients that we need. If I want to measure the inner product between two tangent vectors u and v in the tangent space of M, I can first push them forward to the tangent space of N, and then measure their inner product with the metric G. And I will call that my inner product on M. And this is what we call pulling back the metric from N to M. Now, so this is the pullback from N to M. Now, an example that will be a particular case that will be of interest to us is the case where N is some Euclidean space, for example, the space of activations of my hidden layer, a very high dimensional space. And in that case, a metric of interest is just the Euclidean metric, so the Euclidean dot product. So in that case, if I want to measure the inner product between two tangent vectors in the tangent space of M, I can first push them forward to the tangent space of N, and then just take their dot product, so the transpose times the other vector. Now, I can do some additional algebra. So if everything is given in local coordinates, so the transpose of product is the product of the transpose, and I get a matrix G, which is the Jacobian transpose times the Jacobian, which is an SPD matrix, and which is a local coordinate representation of the pullback metric. So now I have narrowed down the problem of understanding the geometry inherited by M from N to understanding this this symmetric positive definite matrix. Okay, so we have defined our pullback metric. And now we can understand a little bit better what we were seeing at the beginning in terms of inner product and distances that I've discussed at the beginning. So we have an inner product between tangent vectors. We therefore have a norm, which is just the inner product of a vector with itself and then the square root of that. And so we can define distances between points along the manifold, which characterize the intrinsic geometry of the manifold, in terms of the minimal length that the curve going through those 2 points can have. And by the length of a curve, we mean the integral of the derivative of this curve, the norm of the derivative of this curve. So here we really have all the ingredients that we need to now try to define a similarity metric between different manifolds. So back to our neural networks. So the setup I'll consider is the following. So I have a feed-forward network that receives input data on a manifold M, and this manifold is going to be embedded in some input space, Rn in. So for example, that could be the pixel space. And then there are 2 maps, one that the map phi that maps this input space to the hidden layer activation, and then a map zeta that maps eta that maps Rn to the output of the network. And since we're only interested in the hidden layer activation, I'm going to focus on this map phi and ignore the decoder part. So now to define the pullback metric of a network like this, so I can take 2 tangent vectors in my original input manifold M, and then push them forward to tangent vectors in my input feature layer, the pixel space, and then push them forward to my activation space Rn, and then just take their dot product there. And this is going to be my pullback metric. So schematically, how does that look like? So I have my input data manifold M, and I can take 2 particular tangent vectors, v1 and v2. I can push those tangent vectors to the pixel space, to the data feature space, and then push them forward to the network activation space. And then at that point, I can just measure their inner product as the Euclidean dot product between them. And as we've said in the previous slide, this dot product is summarized by this G matrix, which is a symmetric positive definite matrix, which I've shown a particular example of here. And now we can pull back this inner product to the original input manifold and compute, for example, geodesics. And if we do that, we can see that we get a new geometry on the original input manifold that is capturing the geometry of the hidden layer activation. Okay. So now we've kind of went one step towards defining a similarity metric between neural networks from the point of view of Riemannian geometry, in that we've characterized the metrics of our 2 networks. And so the next step is going to be to define a distance function between these metrics at one particular point. So if I have 2 SPD matrices, G1 and G2, that are the local coordinate representation of the pullback metric in my 2 different layers, in my 2 different networks, how can I define a distance between these SPD matrices? So for this, we can first notice that the pullback metric is an SPD matrix, as I've mentioned, and there exists standard metrics on SPD matrices out there. However, they are not very suited for similarity analysis and for understanding neural network activation, and for various reasons. So you might be familiar with the affine invariant Riemannian metric, AIRM, or the Hilbert metric on the SPD cone. But these have features that are not very useful or undesirable for similarity analysis between neural networks. So for example, the ARM is not scale invariant. So if you have one network that is just a scalar multiple of the activation of the other network, you would expect that that would report a distance of 0 but here it won't be the case. And both of them are not bounded, so you can get any positive real number, non-negative real number out of them, so it's not easy to interpret what the numbers reported by them mean. So instead, we'll define a new measure between the distance between SPD matrices, and the way we are going to do that is via a generalized eigenvalue equation. So why generalized? So here, if G prime is the identity matrix, you recover the usual eigenvalue equation. But in general, here, G prime is not the identity matrix. And so we can find the vectors and lambdas, scalars that satisfy this generalized eigenvalue equation. And we define the spectral ratio as a distance between the two SPD matrices as 1 minus the square root of the ratio of the smallest to largest generalized eigenvalue. So naturally, this number is going to be between 0 and 1 because the smallest generalized eigenvalue is always smaller than or equal to the largest generalized eigenvalue. And so we now have a new way to quantify the distance between SPD matrices in terms of this spectral ratio. So what we prove in the paper is that it is indeed a proper distance, so it satisfies symmetry, the triangle inequality, and so on. And it has several desirable properties for similarity metrics, and in particular, solves some of these issues that the ARM and the Hilbert metric had, in that the spectral ratio is invariant to rotation and scaling, and it is also bounded. Okay, so back to our picture, to our goal. So we had our two networks that we wanted to compare. We said that we can compute the pullback metric pointwise on the manifold, and we've defined the distance between these different metrics pointwise between SPD matrices. And now we want to have a way to quantify the overall distance between all these metrics over the whole manifold. And so for this, what we are going to do is just to compute a sort of average spectral ratio over the whole manifold. So I'm integrating over the whole manifold the distance between the local coordinate representation of the pullback metric of these two networks. And then I'm dividing by the volume of the input manifold. And there is a way to make this notion of averaging precise from a statistical standpoint, but I won't go into this deeper. So now we have a way to do similarity analysis between neural representations, between Riemannian manifolds, in terms of this distance, this DMSA distance. And importantly, now this distance just takes two functions as inputs and can compute the distance between their induced pullback metrics. And just to make that clear, so here this distance is also between 0 and 1, so we can immediately define a similarity metric as just 1 minus the distance between the two network representations. So in the paper, we prove several additional properties. So we prove that MSA is a distance on Riemannian and statistical metrics, information geometries. So it satisfies the triangle inequality and so on, but between Riemannian manifolds. It's scale invariant and state space rotation invariant, as well as a few additional properties. We also derive some estimation bound on MSA. So when you don't have access to the exact manifold or the exact function, how you can bound MSA or understand the error in the MSA similarity. And we also derive a relationship between the Kramer-Rao bound and MSA for statistical manifolds specifically. And I'll discuss a bit more statistical manifolds in the next couple of slides so we can understand that better. Okay, so now we have our method. So metric similarity analysis enables comparing the intrinsic geometry of two manifolds. So we can compute the pullback metric and then average it over the manifold. And that gives us a number between 0 and 1 that quantifies the similarity between these geometries. So now, having defined this new similarity metric, I'm going to show a couple of applications. So if you're interested in more technical details about how to compute the manifold, how to compute this integral, and so on, you can look at the paper. And I thought instead for the remaining time, I would show a few applications. So first, I'm going to show an application to feature learning. So it turns out that you can train a network in different learning regimes. So the same network, same architecture, same inputs, um, but by varying some hyperparameters of the network, you can make the network either generalize or not. And we call that rich networks or lazy networks. And the toy model that I will consider for this is the following. So I'm going to consider one hidden layer MLP that receives inputs on a two-dimensional manifold. So here, the input manifold is the full input space, which is just two-dimensional. And the network has to classify into one-hot encoded vectors these different points in this plane. So the first thing that we could do is just ask what the extrinsic geometry of these two networks look like. And so one way to do that is just to apply PCA to the activations. And if we do that, we don't see much. They look quite similar. And if we want some more quantitative measure of that, we can do procrustes. And in particular, here I've done procrustes between the rich network and a rich network of another seed, rich 2, or the rich network and the lazy network. And in all cases, the similarity is very, very close to 1. But if I look at the geodesics under the pullback metric of my two networks, they do look slightly different. There does seem to be a difference between the rich and lazy network. And if we quantify the difference between the intrinsic geometries of the two networks with MSA, we do see a difference. The rich and lazy network are dissimilar. So this is kind of a simple example into what we mean by understanding the similarity between the intrinsic geometries. It can be important. So to be slightly more systematic, next what I'm going to do is create many, many more rich and lazy networks. And I'm going to continue or more systematically vary the hyperparameters of the two networks. So I'm going to train rich and lazy networks. I'm going to consider networks that are pre-training or after training, and networks that are trained on the 2 classification task or classification task with 5 classes. And what I will do is compare or perform similarity analysis between this reference model, so a lazy network after training on the 5 class classification task, to all these other networks. And if I do that, what I see is that the similarity between the networks is strongly correlated with the number of hyperparameters that they share. So if all the hyperparameters are the same, then they have a similarity close to 1. And as I continuously change this hyperparameter, the similarity decreases and decreases. But that's not the case for all methods. So for example, CK and kernel CK, they don't seem to capture a difference between these two networks. So lazy networks trained on a 5-class classification task or rich network trained on 5-class classification task. And some measures, they don't really make sense. They say that this one, which has less hyperparameters shared, is more similar than this one to the reference model. So really understanding the intrinsic geometry of these representations is more insightful. And just to show this result in a different way, so here I've just shown the similarity between any pair of network as a matrix. And we can really see the structure where the fewer hyperparameters these networks have, the more dissimilar they are under the MSA similarity. But if we look at other similarity metrics, it's not so much the case. RSA can't really tell apart those networks, and CCA doesn't seem to have the right structure, this correlation with the number of shared hyperparameters. Okay, so the second application I'll consider is a deep convolutional network, a ResNet. And so a classic analysis in these mechanistic interpretability and geometry papers is to compare the geometry of different pairs of hidden layers. So I'm going to consider pairwise similarities. And So I'm going to consider different inputs, different images. And to construct a manifold, what I will do is use a pre-trained VAE. So I'll pass those different images through the VAE. These will correspond to different points in the latent space of the VAE. And then I'm going to interpolate between those points to create a simplex manifold, and perhaps also add noise to those points, and then pass them through the decoder. And at that point, I have a nonlinear manifold in pixel space that I can pass to my ResNet. And importantly, I'm going to choose these different images to be part of different classes because this ResNet is trained on a classification task. Okay, so here is the similarity matrix between different pairs of layers. So we can see that along the diagonal, so the similarity between a layer and itself is always 1 and continuously decreases as you go from one layer to the next. And it's not so much the case for other methods that are based on the extrinsic geometry. We can also look at the effect of noise, like I said. So here in red, we have MSA, and the other two curves are CKA and kernel CKA. And we can see that MSA is very robust to noise. So if we add noise to the manifold, the similarity doesn't change much. Whereas these other metrics based on the extrinsic geometry, their similarity varies a lot. Okay. So finally, I'll briefly present results to extend these to statistical manifolds. So what is a statistical manifold? So it is a family of distributions. So now my models are probabilistic, and each point on the manifold corresponds to a particular distribution of output of the model. So yeah, that's what I just said. So for a particular sample X, we can consider the log probability map, which is a map from this manifold M to the real numbers. And then we can ask what the pullback metric of this log probability map is. So I can compute the Jacobian of this log probability map, which is just going to be a row vector. And then I can compute the pullback metric, which is just going to be the Jacobian transpose times the Jacobian. So here, because the Jacobian is just a row vector, it's just an outer product of vectors. And then if I take an expectation over the particular samples X, I just get the Fisher information. So the expected pullback metric of a probabilistic model is just the Fisher information of a model. So another way to see it schematically, say I have a parameter manifold that defines the mean and the standard deviation of my probability distribution of my model. I might have two different statistical models, for example, a Gaussian model and a Laplace model that have different densities. And then these different densities will have different Fisher informations, which correspond to different geometries. And here you are looking at geodesics under these geometries. And then we can compute the pullback metric pointwise and so on, and just compute MSA between these different statistical models. So how can that be useful in the case of AI and machine learning applications? So for this, I'll show a diffusion model. So I won't go very deep into what a diffusion model is, but in short, a diffusion model is a way to transition from a noise distribution, here Gaussian, to some data distribution by taking samples and flowing along some flow field defined by this vector field F. And in particular, what I will be interested in is so-called conditional diffusion, where this vector field not only depends on the point X in this space of images, but also on some conditional input that, for example, tells the model generate an image of a cat. And the way I'm going to define a family of models is by doing a bilinear interpolation in the text embedding space. So I'm going to take 4 prompts, green leaf, green branch, blue leaf, do a bilinear interpolation, and then get a manifold where each point on this manifold corresponds to a full distribution of possible images that the diffusion model can generate. So here on the right, you are looking at individual samples along this manifold of the diffusion model. And so we can gain several insights from this, but I'll show just one, which is that if we compute the similarity between the manifold at different time points of the diffusion, then we'll see a progressive change in the geometry. So as the diffusion time increases, the geometry will continuously change. And so here you are looking at the similarity matrix on the right, and then I did an MDS, multidimensional scaling, on this matrix to look at the curve in 3D space. Okay, so with that, let's summarize all this. So first, at the beginning, I said I wanted to define a distance between neural network representations, a distance in mathematical terms. And additionally, I wanted my distance to be aware of the intrinsic geometries of these manifolds. And MSA is able to do that. And finally, I showed several examples where MSA was able to capture some of the computational mechanisms that the network was using to perform a task, or were correlated with some hyperparameters of the network. So if you're interested in these kind of ideas, I have several other papers and projects on this. So if you're interested in this dynamical system angle, so vector fields, flow fields that I mentioned at the end, we have this NERVS paper at the top where we go very deep into the pullback metric of these systems. If you're interested in the rich and lazy example, we have another paper, the one in the middle, where we study generalization and how that relates to the intrinsic geometry of representations. And we also have an upcoming paper about generative models, where we study mode collapse, also with similar ideas. And with that, I would like to thank my collaborators on this project and adjacent projects, and everyone who gave feedback on this project. And I would also like to very briefly advertise some upcoming positions that I have. So a couple of RA positions and also a PhD studentship into very similar ideas, so using tools of Riemannian geometry to mechanistically interpret the computations performed by neural network. Thank you.